and welcome back. Now let's have a discussion about some of the issues of floating point. So first, there's some fallacies we want to dispel. Is add associative? Addition should be associative, right? That's 1 plus 2 plus 3, whether you add the 1 and 2 first or the 2 and 3 first, it should be the same number. It should be 6. Well, is that true for floating point add? Here's an example. So let's make x a really small, a really big negative number. So minus 1.5 times 10 to the 38. Let's make y exactly the opposite, but a positive number. And let z just be 1. And we even saw how to do 1 in a previous video. Let's first add y and z together. Well, when you add y and z together, you get this really big number and this really small number. And the number of bits that you can play with is really 23 bits total. If you include the normalization, there's like 24 total bits from like leftmost bit to the rightmost bit. That's a 1. And the problem is you don't have enough bits, at least in the floating point and a float, to store both the 1 and this really big number over here. So you can't do that. So when this rightmost, let me get my thing, when this adds together, that 1 goes away. I can't store this 1 and that 1. The bigger one wins. We lose the 1. Well, that means it's as if the z wasn't added at all, and I get x plus y, which is 0. Well, now let's try it again, seeing if it's associative or not. Let's try the leftmost one. So the leftmost one says, here the leftmost guy and x and y, and they cancel. And then you have 1. And so these two are not equal. So therefore, in summary, floating point add is not associative. Really important that you saw that. And the reason for that is you just have a fixed number of bits. You can't do more than that. If you have a really big number and really small stuff, you can't keep both those guys alive. You could imagine a third. Maybe you wanted to invent a third way to have big numbers and small numbers and have 2 pieces of them. And I mean, that's kind of like having 2 separate numbers anyway. But a single number can't be both really big and really small. So this bullet says exactly what I said. The number is so much bigger than 1 that the representation cannot store both of them at once, and so it loses it in one, keeps it in the other, because they cancel each other out, and 1 is not equal to 0. I wanted to give you a definition, just so that you're using the right words as you're talking about floating point numbers. So precision is, if this is any representation, it's the number of bits we're throwing at the problem. So precision, oh, I want more precision. Throw more bits at the problem. Oh, okay, float only has this number of bits. Well, double that or quadruple that. You'll get more precision. The more bits you have, the closer you can get to the actual number you're trying to get to. Accuracy is the distance between any number that you have coded and the original actual number. So here's an example. High precision, a lot of bits, permits high accuracy but doesn't guarantee it. Here's an example here, float pi equals 3.14. Well, there's going to be lots of bits, 32 bits associated for that, but you're still pretty far in terms of accuracy from the actual value of pi. Now, you could have done more. I could have initialized it to a closer number, but that particular example says I got a lot of bits, but it isn't close to the actual number. So that has high precision, low accuracy in that case. Now let's talk about rounding. So rounding is this complicated thing where you're doing some calculation and then you figure out, okay, well, I'm not exactly at one or the other. I'm not exactly at a floating point number. So do I go the one above or the one below? That's the idea of this. And there's some hardware that usually carries with, usually floating point hardware has a couple of extra bits on the far right side that's called rounding bits. And those extra bits can be used to figure out where do I really want to go, the floating point number above or the one below in terms of that. So this is the 32 bits, and there's extra bits on the right side of that that's useful. So there are modes. When I'm in the middle, let's say the rounding bits say that there's something in here that's not a 0 down here. My rounding bits means there actually is something to the right of that. There's 4 rounding modes. You could either round always toward positive infinity, always to the right on the number line, or always to the left on the number line, always towards minus infinity, or just truncate it, which actually means always rounding it towards 0. Or, here's the more clever way, you could have it in an unbiased way. Rather than always bigger or always smaller or always towards 0, you could sometimes go up and sometimes go down. And that means when you're midway, Well, by the way, these examples I'm showing you are all examples in decimal. This is not the same as binary, but you obviously were working with binary and we're working with floating point calculations. So in the first example, you round up, that means 2.0001, well, you round toward the next guy. That's in the middle, between 2 and 3, that would round up to 3, okay? And -2 would round to 2, we always round to the right. The same idea, always round left, 1.999 rounds to 1, even though you're almost at 2, you go back to 1, you lose it. And -1.99 also goes down, also goes negative. So here's the case when you're in the middle. So normal rounding, 2.4, again, this is in decimal, is less than halfway, so it would round down to 2. 2.6 would more than halfway, would round up. 2.5 is exactly in the middle. So that was going to round toward the even number. So that rounds to 2, but 3.5 would round to 4. Nice. So think about this. I've got some binary equivalent of this, but this is now in binary. So I've got some binary numbers here, okay? 0, 1, 0, 1. Here are the rounding areas, okay? So now, what's halfway between this? By the way, if I have many bits here, let's say I have 3 bits. Let's just say I have 3 bits. Those bits would be from 0, 0, 0 to 1, 1, 1. What's halfway in the middle in binary? Well, remember what half is in this? Yeah, it'd be a 1 and zeros. That's halfway in the middle. So when you're that way, that's when when the rounding bits are 1 and all zeros, that's halfway in the middle. And then you're making a decision in this particular mode, which way to go. Well, you round toward the even number. So you ask, is that an even number? No, that's a 1, that's an odd number. So therefore, I'm going to round not toward that number, but toward the one above, and that would round up. So this would round to 0, 1, 1, 0, okay? If I had 0, 1, 0, and then here's the rounding guys, and now we're 1, 0, I would round toward the even, I would round down, which means round down toward the even, and I would just cross it off, and that would be the closest even. Does that make sense? So you round toward even in binary, which means you have to be a 1, 0, 0, 0, 0, 0, 0, 0 in the rounding bits, and you round toward the even number. If it's a 1 there, you round up, you add 1 to it. If it's a 0, you just truncate those rounding bits, okay? That way we kind of round both ways. And we really like that as a default mode, so that's the default mode for the system because it kind of is fair. It doesn't always go make things bigger or make things smaller. However, IRS, if you're calculating my return, can you round up always? Just don't round in the middle. So now you know when you see these errors. Here's this wonderful comic strip I found online. And here is a robot, and it says, welcome to the secret robot internet. Prove that you're a human. 0.1 plus 0.2. 0.3, 4. We can represent powers of 2 perfectly, fractional powers of 2 perfectly in floating point, because it's 0 in the significand and some value of the exponent. Because we're decimal, we can't do 0.1 or 0.2 very easily because it's 1/10. This 10 thing is different. These 10 fingers are the problem. So this is an example of 0.3. If you type 0.3 into my simulator, you get 0.3000, and it's not exactly 4, maybe that's a double, but in the float, in a single precision, or 32 bits of a float, we get 0.3001. So this is exactly why you would see this error. Addition. Let's talk about addition now. We're just talking about elements of this, rounding and addition and truncating and all those things. So addition is a little bit harder because you can't just add the significands. You have to denormalize to match the exponent. You have to kind of line them up, okay, to match the exponents. Then you add the significands to get the resulting guy, and then you have to keep the same exponent and then normalize to get the end. So you have to kind of shift it, do something, and then shift it back whatever the result is. They may cancel each other out to make something, you may have a big number and a big number, but it turns out that they cancel most of the big stuff and the small values are what's left. Then you have to renormalize to get that right. If the signs differ, you just do a subtraction instead. This is how you do casting. You've seen casting when you do Malik. When you go to the Godfather, you have to cast that uninitialized void star space into whatever type you want so that you know pointer plus plus knows how much to jump. That's the reason we do that. And also to check whether you're matching these right and everything, the pointers work out. Type checking, obviously. Here, if you've got a floating point number you want to convert to an integer, you just say int. If you remember in Python, it was int parentheses. There's a function call to that, there's a method call to that. Here you just typecast it with the parentheses int. So here's 3.14159 times some float, that's obviously a float, and now you cast that to an int to see what the closest integer that might be. Conversely, you do the same thing on the other side. If you have an integer number, you want to float convert it like that. So you say float of that integer expression, and now you're able to work with that. So if I have f as a float, and I want to f plus equal another float, well, if I have I, which is int, you have to convert it to a float so that the compiler will be happy. So now you might ask yourself, well, if I go from an int to a float back to an int, do I get the same number? Does this always print true? Pause the video and think about it. Talk to your neighbor. And then come on back. And we're back. If I equal int of float of I, same thing? Ain't no free lunch. There are integers that the float can't handle. So there are certain integers. In fact, I even showed you one. I think it was a little bit more than 16 million. That has no float equivalent. You know you can count up to 4 billion in floats, in integers, unsigned numbers. Well, floats, the first number you can't do, we saw that before, 16 million plus 1. I can't do that number. 16 million plus 1 that can't be done. I mean, 2 to the 14, 2 to the 24 plus 1 can't be done. I showed you before. So, we do that, it's going to snap it to the closest float. When you go back to int, it's the back in the same int. I can do that. It'll either be, now think about rounding modes. That number is 2 to the 24 plus 1. Can't be done. So does it snap to 2 to the 4, does it do 2 to the 24 or 2 to the 24 plus 2? Well, this is an even number, so it'll round to even. So that's an exact case of that rounding mode there. That's going to be 2 to the 20. Try it. 2 to the 24 plus 1. See what it says. That'd be really fun to play with, okay? Can't be done, sorry. Double precision. So let's talk about double precision. Could that do it? You want to ask yourself, look at the double precision. Could double precision do that as well? Float to int to float. Does this always return true? Pause the video and think about it and come on back. And we're back. Ain't no free lunch. What if the float is 1.5? This is the easiest one, 1.5. Obviously, there's no int that does 1.5, and you go back, it's going to be the integer representation. That'd be either 1 or 2. What do you think it does? 1.5. Round to even. The closest even number is 2. So that should, in theory, be 2 when it comes back. So that should not be the same. That's an obvious one why that doesn't work. We'll see you in the next video.